Good afternoon. Welcome to the distinguished webinar series organized by the Canadian Association for Earthquake Engineering and Seismology. My name is Mertash Motamedi from the University of BC, and I'm going to moderate this session. Today, I'm very excited to introduce Dr. Sherry Molnar from the University of Western Ontario. Dr. Molnar is Associate Prof conducting earthquake hazard research focused on seismic site characterization and earthquake ground motion prediction using physics-based numerical wave propagation simulations to account for local seismic site effects in seismic hazard assessment and mapping. Sherry continues to serve on seismic design committees of the 2020 and 2025 Canadian Building Codes, is a former director of the Canadian Association for Earthquake Engineering and Seismology, and former president of the ERI British Columbia Regional Chapter. Dr. Molnar is presenting the Metro Vancouver Seismic Microzonation Mapping Project today. So I would like to invite her to start the presentation. Sherry, please.
Okay.
All right, I think we're set up and ready to go.
Yep.
Great, thank you. So as Murtash said, I am an associate professor at Western, and my name is not the only one on this slide, in that I'm here today to present to you the work that has been happening in this seismic microzonation mapping project for 7.5 years. And so it's not just me, it's a team of over 30 individuals who've been working on this project. The biggest names up on the list here are research scientists, associates, postdocs, and PhD students that were involved in the work, and then smaller fonts for master's students and undergraduate students and research assistants that helped us with the project. So it's not just my work that I'm showing you today. So our project is a near-decade project that's been going on since 2017. And the focus or goal is to generate a whole bunch, a suite of region-specific seismic hazard maps. It's particular to Metro Vancouver. And there's been a phased approach to the inclusion of the communities in Metro Vancouver. In 2017 and 2018 into 2019, we were only focused on the Western communities. And now closer to the end of the project into 2026, we're working on the most eastern communities of Metro Vancouver. These maps basically are a way to display the predicted variation in earthquake hazards primarily due to local site conditions, or how can the ground alter earthquake shaking or disrupt or create differences in the amplitude of the shaking, the duration of the shaking, whether it can trigger landslides or liquefaction, are all associated with detailed local information that gets put into seismic microzonation maps. So this project is funded through the provincial government, emergency management and climate readiness. Specifically, we've been asked to produce maps that will depict shaking amplification, or how much will the ground alter earthquake shaking due to the waves interacting inside of lower and lower velocity material or soils as it gets close to the surface. This, in terms of geotechnical or earthquake engineering speak, is one-dimensional site amplification. We've also been asked to include the shaking amplification that will result from waves interacting on the three-dimensional Georgia Basin structure beneath Metro Vancouver and offshore. We've also been asked to produce maps that will depict landslide susceptibility and liquefaction susceptibility and push to the hazard of it, or the hazard potential of these two geotechnical failures that might be triggered by the seismic shaking. Last to say is we don't look at topographic effects, we don't look at tsunami. Our maps are particular to shaking and the effects of that shaking to geotechnical failures of liquefaction and landslide. In order to do that, we got to know a lot about what the subsurface ground conditions are like in Metro Vancouver. And you wouldn't believe, but there's not an open repository of geodata beneath Metro Vancouver. It had to be assembled and compiled. And it took us many years to do so, first by looking for available information online, usually from provincial and federal government sources, and then also talking to those who have collected geodata in the past and asking them to share access to that data through data sharing agreements and for the purposes of seismic microzonation mapping. In the end, we created a geodatabase that has information about subsurface ground conditions at over 15,000 unique locations. In complement, the project also funded for me to take some students every summer for 5 years to collect seismic recordings on the surface of the ground. And if we use one seismometer, we can find out what kind of the amplification spectrum is like at a location through this MHVSR. And that can be accomplished pretty quickly in 30 to 60 minutes. We can do that with one seismometer. So we did that in a grid about 800-meter spacing and collected those measurements at over 2,000 locations across Western Metro Vancouver. We also targeted seismic testing at over 120 locations, which are the black triangles. And there's not a lot of them necessarily in the Fraser River Delta, where we already knew a lot about the velocity structure in soft sediments. We were really targeting those areas of glaciated material that's hard to penetrate through invasive testing and really is important to try to capture through non-invasive or seismic propagation of waves. So in conclusion, this is a relatively cost-effective approach that the project invested in making sure there was good coverage of geodata from surface measurements, but then also complemented with very high detailed, very high resolution, every meter measurements from invasive testing. And we wouldn't be able to understand subsurface ground conditions without these two vital main pieces of geodata, both invasive measurements and non-invasive measurements. In one graphic summary, we were tasked with making seismic microzonation maps for these three hazards, shaking, and then the effects of that shaking to liquefaction and landslide. So I mentioned we made a big new geodatabase, and that allows us to be able to figure out what the stiffness of the materials are, what the site period is, or the depth to the rock. This is unusual in that, people ask me, can this data set be used for flood mapping? Flood mapping is very superficial or very based on topography. Whereas for seismic, we need to know the information about the subsurface in detail all the way through the soil that's going to amplify those shaking. And it's a much more complicated problem or deeper need for creating seismic hazard maps. So geodata is deeper than most types of natural hazard mapping. Once we had our geodatabase, we would then be able to make or express that geodatabase in the forms of maps. We can create maps of any of these metrics that are inside of the geodatabase, but then we also needed to have these ideas of what that data is like at any given location from which to then push to produce the hazard potential maps or the hazard mapping, which then has to be dependent on the level of shaking intensity, which is coming from the 6th generation National Seismic Hazard Model or the 2020 Building Code. So now that I've introduced you to the project, let me explain a little bit more about seismic microzonation mapping. I hope everybody knows that if you feel an earthquake, how you experience it could be very different from somebody else a few hundred meters away. And that the reason that normally happens has to do with the local ground conditions. It's the same earthquake, so the same magnitude. You're close to each other, so the distance apart shouldn't attenuate the seismic waves too much. But for some reason, I experienced it like a rapid vibration because I was on rock and you're on soft, thick soils and you felt like it was swaying and rocking. That's side effects. And we want to capture that or try to depict how that will vary for emergency planning purposes and other end use cases. So seismic microzonation is a verb, it's an action, it's a process that we subdivide zones into similar seismic hazard. And that's very focused or targeted on how it will vary because of the subsurface ground conditions, how they alter that seismic energy. And so this is normally accomplished at regional or urban scales or for a city. And then something I didn't appreciate necessarily at the beginning is that I'm a seismic hazard expert, and it's an interesting aspect that to make a map, it helps me communicate the technical seismic expertise behind what is being tried to be portrayed. Another way of thinking about it is that presumably we're all used to or familiar with the fact that the federal government makes us seismic hazard maps every 5 years as per the building code. Those Canada is a huge country, and so we pretty much treat the ground conditions as the same across the country. And then we use site amplification inherent in the ground motion prediction equations to kind of adjust what the level of shaking would be for site conditions that are dependent on one parameter, VS30, the shear wave velocity in the top 30 meters. Everything about how the ground will alter earthquake shaking gets put into one parameter inside of national scale mapping. And then on the very other end of the scale is you could be a geotechnical engineer doing dynamic response analysis for your particular site. And these two things are very far apart in terms of providing very accurate ground motions or reducing the uncertainty around what the ground shaking would be because you don't know a lot about the subsurface ground conditions. And so microzonation mapping is somewhere in the middle. We're doing better than a national scale map, but we're using geostatistics or trends in regional trends to try and fill gaps between sites. But our maps are dependent on basically site-specific seismic hazard at many, many, many sites. And that's how we make the maps. One more aspect about seismic microzonation mapping is that not all maps are the same. They're not all the same caliber. And so in international guidelines, they talk about at least 3 levels at which maps are made. At the first level, you could download a spatial data set online, and as a geography student assignment, you could complete a seismic microzonation map. But of course, as you increase the quality or the quantity of what you know about the site, you can push to improve the spatial resolution of the mapping. And you can also push the sophistication of the analyses that's being accomplished. Somewhere between level 2 and 3, the shaking intensity has to be part of the analysis or included. Level 1 and level 2 maps might not even care about how strong the shaking was. It's just trying to say how susceptible the ground is to shaking amplification or liquefaction. But by level 3, it's conveying how much liquefaction or how much amplification might happen because of the level of shaking. A seismic hazard analysis has been performed by the time you get to level 3. And so, of course, the more sophisticated the analysis and the more data that you use, it will cost you more and it'll take you longer. So it's taken us 7.5 years, and the project is funded with $4.41 million. And so we pushed to level 3 to make seismic microzonation maps for Metro Vancouver. Also, in the literature about seismic microzonation maps is that they're supposed to be really helpful to everybody. But I would argue that the more I talk and produce these maps and share them, more and more end users don't really know what they're looking at. And so I would say technical experts like you joining me today, who are earthquake engineering professionals or in our community, are supposed to be using these maps and understand that they're readily easy to use as input for the next step, be it risk analysis or risk reduction or retrofits. And intermediate users are those who don't have seismic hazard expertise or training, but they're in the role that they're in charge of assets or community planning, and they have to make a decision, and they have to try to have access to information to make that decision. So it's great that these maps are being produced, but what's the investment in time by an intermediate user to try to understand these maps? One more piece of background information is, let me tell you what it's like in Canada. So our seismic microzonation maps have been available since the late 1990s. presumably you might have seen one or two over the years. They're available online, usually from collaborations through academia and federal or provincial governments. Of course, there are some private or paid for by contracts to just engineering firms, and they may or may not be publicly available. Another key piece of information is that they've already been accomplished for the highest seismic risk cities in Canada. But there are no maps that are available in a digital form. You can't play with them. You can't also merge them with your assets and perform a risk analysis quite quickly. All you get is a static map image, like a PDF or an image online. Last but not one of the other major things to share with you is that all the maps shown below are trying to basically express seismic site class, or generally what the VS30 or this susceptible metric to site effects is for these regions in Canada. More and more, we're seeing that the maps are shifting away from seismic site class, which was last used or needed in our 2015 building code. And now we're starting to see maps being produced for the VS30 metric itself, which is the new metric effective in our 2020 code. And we're starting to also see additional maps being produced, like site period. One other key piece is that you can see the maps are technically all supposed to be displaying the same thing, but none of them look the same. There is no standard for how you make these maps. And that's a problem, because that's one of the most major hindrances to us comprehending these maps quickly. I can't look at all these maps very fast and say, oh, that's site class C. If we all agreed site class C should be green, then we'd be able to do that quickly. And our project has pushed to make these a whole suite, 18 maps of these level 3 seismic microzonation maps that have never really been accessible before. And we're not sure how successful a product it's going to be to the earthquake engineering community. We're going to find out. Last thing to share with you is that currently there's work happening by NRCan seismic risk modeling team to merge what has been acquired as level 2 seismic microzonation mapping of VS30 in these regions in Canada with a more blanket level 1 topography-based VS30. So a mosaic VS30 map is under development, and what should be available for all of Canada in the coming year. When we started the project, I assumed people knew what seismic microzonation mapping was and that they were really using these maps. But we ran an online survey in 2020 to ask those in the earthquake engineering community, are you familiar with the seismic microzonation term? Do you use these maps? Are you aware of these maps that are available in Canada? And a lot of people filled out the survey. We had 100 people, but we asked 54 questions, so it was hard, and only 58 people eventually filled out the whole form. But what we found here is that non-technical end users are just as familiar with the seismic microzonation mapping term and the maps, but they don't use them like our technical end users say they do, or to the same level. Overall, it was communicated back to us that the audience or our community is not satisfied with the level of seismic hazard mapping that's available in Canada. And I would say I found out that there's a relatively decent familiarity with the maps in Western Canada, but it's much lower comprehension and use or familiarity for Eastern Canada. And this parallels probably the perception of seismic hazard and risk and the uptake of insurance. This is very similar situation. We even went so far as to show people maps and ask them to interpret them. And of course, technical users were the most successful at interpreting our maps. That's great. But for the more questions we asked, we started to see less and less comprehension. And again, it's this evidence that if we standardize how these maps were being made, it would help alleviate trying to train people to understand everybody else's new map every other time it's made. Lastly, I need to point out why it's so important to do this work for Metro Vancouver. I assume everybody here is very aware that Metro Vancouver has the highest seismic risk in Canada, which is driven from the active subduction setting and the frequency and occurrence of earthquakes. But also there's this really cool and challenging feature that the geology is very variable in Metro Vancouver. You go from sea level to the high 1,000-meter mountains. And so it's these two things, the fact that there's this high variability in the seismic site conditions and that the seismic hazard itself is not just one source. This is why we haven't made these maps up till now. This is the hardest place in Canada to do this. And so we're pushing to level 3 seismic microresonation maps. So we're going to replace all those little pieces of previous maps that have come before for just one or two little cities or communities. We're also going to make sure we do it all at once in the same way for the whole region, all together, so that the same quality of map product is available for all of Metro Vancouver at once. And we're going to try to standardize or establish a standard that we might be hopefully going to use moving forward in Canada. Rather than wait to the end, I'd rather tell you about the cool, awesome things that got produced by the project. And so one was that we're pushing to this level 3 in seismic microresonation mapping. Never been done before at this level or in this comprehensive or this many in Canada. We also are in need of a standard and a need for the earthquake engineering community to uptake what we've produced. And so we were partnered with engineers and geoscientists of BC to have a technical peer review and also to develop professional practice guidelines to development and use of seismic microresonation mapping, which is great steps towards a Canadian standard. And lastly, why do a project for 10 years and wait to the end to tell people about it and be like, ta-da, here's this map we made, hope you use it. It's much more important to stop and talk to people along the way to find out if what we think is the right thing to do is helpful or going to be useful for the purposes that these maps are being made for. So those three main aspects that we're after, or these key purposes that happen throughout the project, we developed this geodatabase, and it also allowed us to renew and advance what we knew about subsurface ground conditions in Metro Vancouver. We could now convert from one data type to another. We can plunk down a seismometer, which gives us one measure, but through relationships that we compare that measurement, we can now convert what we actually measured to the metric of the depth to glacial sediments. We had to push and build these relationships from our geodatabase and ultimately develop a detailed picture of the subsurface ground conditions, or essentially a three-dimensional structural or velocity model for the region. And of course, we should stop and check with recorded earthquake data and also verify whether our numerical modeling makes any sense with earthquake data that's out there in the world. And so there were pieces of that going on through the project. These are expressions of measures that are inside of our geodatabase. And so it's not like we didn't know anything before, but we primarily knew that for the Fraser River Delta region, and we didn't know it for all of Metro Vancouver. So not only do we update what we know, but we also spread out further the comprehension of those measures. And we also, for the first time, have a picture of what site period is from 2,300 measurements across Metro Vancouver. And we've also been able to see the trend in the velocity in glacial sediments. And that wasn't available before our project started. Again, seismic is, we got to know how the waves are going to propagate all the way to the surface from rock. And rock can be quite deep in the Fraser River Delta, like almost a kilometer. And invasive testing would often find glacial sediments are good foundation and stop. And so we didn't know the trend of the velocity in glacial sediments without the advancements that happened in our project. One really key output of our project also was that engineers and geoscientists of BC developed these professional practice guidelines. They're available online through the Engineers and Geoscientists Guidelines repository website under natural hazards. These guidelines are for a common approach to developing maps as well as the use of these maps. And so if you're a practicing engineer or a mapping professional in Canada, these guidelines should be very helpful towards how you should incorporate developed microzonation maps or how you should help make a seismic microzonation maps in future if you do so as a contract. The third key piece that was happening for this project was that we were talking to people. And so early on, we would have progress updates, or we'd have a workshop that we would discuss metrics. In 2023, we had a special session for Canadian earthquake engineers. And then into 2024, we switched from talking about maps that we're going to make. And then in 2024, we had made maps. And now it's about education and training about the maps that we have created. And so I've been involved in the last year in about trying to attack sharing or discussing the maps that we have made in about 17 events, or spending about 77 hours trying to educate about the improvement in seismic hazard mapping through the project. And so we've reached a variety of audiences who may or may not interact with these maps. One last way to express a wealth of something that happened in the project is that there's a new generation of trained earthquake engineering professionals who are going out into the workforce, who have had the experience of coming together and working on this project, looking at geology, geophysics, geotechnics, and also a wide variety of experiences. And they bring that now into the workforce. And so that's pretty cool, I think, for the Canadian Association of Earthquake Engineering members who are here today, that the membership, there's this renewal of training about seismic hazard that has spent nearly a decade getting these people into the workforce, which is great. Finally, we get to the point that, yeah, we made some maps. And the ones that we've been released recently is that we've made 29 maps for Western Metro Vancouver for phase 1 of our project area. And 11 of these are what we call level 2 seismic microzonation maps. Or these maps are just depicting susceptibility to shaking amplification, liquefaction, or landslide. This is just telling us where the natural ground is susceptible to these changes. But then I've hopefully sold you on the fact that we pushed, we had data, we had analyses, we considered 2 levels of seismic intensity to ask the question and answer, where does earthquake shaking amplification happen? How much is happening? And then where is liquefaction and landslides being triggered by the considered seismic intensity, and knowing what the slope angle is, or what the soil resistance is at this location. So now, how could you get your hands on them? One is that they've been released through our project data repository online, but also linked through our project website. And we made the traditional map. We made a map. It's kind of a poster-sized sheet that if you printed it, it would look like a poster on the wall. And it's that typical. It had to have a title, it had to have some authors. It explains what the map is mapping. It explains how we made the map. And it goes on to give you a citation, a way to reference it in future. But essentially, we control how the map looks. And this came from the iterative engagement we had over the years. We also heard the audience saying that they wanted access to the digital version of the map. And for the first time, we've released all 29 maps available as digital ArcGIS layer package files. So why we chose that is because the map will load exactly what it looks like from the map sheet. You then have the ability to play around with it and change the colors if you want, although we worked really hard on choosing the colors, and we have reasons why those colors were chosen. But essentially, we want to provide you products that you can use the map as is. We're working with the provincial government, or it's a provincial government funded project. And so they are creating an online web environment that will be accessible to the provincial and local governments, maybe eventually to the public in a simplified form. But currently, this is what it looks like, that there's a landing page, they have explanation overview, and then when you click advanced hazard or susceptibility, you would get taken to being able to see the maps online. And then you'd get some explanation, and you have drop downs of explanation about each of those maps. Not to be outdone, but my Western team has also worked on making the data available through our project website on the open data page. And we've now today launched our map viewer that allows you to look at these maps online as well. So you don't have to download them. You don't need ArcGIS Pro. You can look at these maps today online. I probably don't have any time left, and it's hilarious that I leave not much time for talking about the details. But now let's have a whirlwind tour of the 29 maps that we made. A reminder that these level 2 susceptibility maps are basically answering where the ground is susceptible to shaking amplification, either from the one-dimensional soil column or from the three-dimensional basin. Or is the ground susceptible to liquefaction or landslide? So these maps are simple in that they're just communicating about the subsurface ground conditions, or translate the geodata into maps. And we chose the map metric or value to be mapped, but the geodatabase should be available in the future, that you can make your own map in future as well. Something I'd like to say is that, or emphasize, is that, these maps are not dependent on the chosen seismic hazard or what we know about seismic hazard. It is the geology that controls this. And that doesn't change very fast. And these maps can be useful for a very long time, until such time that more data is available and they can be reproduced or improved. So hammering home the fact that, we are not considering the input of the shaking intensity at this point. It's just trying to express if the ground is susceptible. So we need to start with understanding what the material properties are like in the subsurface, or what the geology is. And the last really great resource that was generated by the federal government back in 1998 was the GeoMap Vancouver poster. And on there, and the data sets behind it, is kind of our last update on these regional scale communication of subsurface ground conditions. And so we started there with our geology map, but new and detailed mapping had occurred into the 2010s. And so we made sure we included and incorporated that. So that triggered us to reclassify the geologic units, and we end up with 55 geologic units that have been reclassified to our system. And so it looks like the Armstrong and Hickok's official geology map, except it's been updated by the Monahan map here. It's been updated by the Blaise Stevens map over here. And also, these polygons or boundaries have been updated on us interpreting the geodata, primarily as we went on to create liquefaction susceptibility maps. So it's not a official geology map. It is a key geology map for the top tens of meters that are important for anticipation of liquefaction and shaking amplification hazards. Once we had a new geology map and an understanding of what the groundwater table is like across the region in map 2, we could push and use our geodatabase to create a susceptibility map of the liquefaction. Again, the old status back in 1998 was just that, if you're close to the river and you're in the Fraser River Delta, it's going to be highly susceptible to liquefaction. And our map is not all that different. It's also still pretty high susceptibility to liquefaction, yes. But we added columns that explain what we know about the subsurface ground conditions in each of these geologic units. We try to summarize how resistive the soil is for those geologic units, and therefore confirm what the liquefaction susceptibility should be. And so it's a slightly more sophisticated level 2 seismic microzonation map product. Then there's this group of maps that basically express the geodatabase. And also it's not just simple interpolation of the data. It also involves the sophistication of geospatial modeling, and that a three-dimensional velocity model underpins what's going on or what that prediction is in any given location. And so we have a detailed depiction of the subsurface ground conditions that was generated for the region at a relatively high resolution, every 200 meters and every 2 meters vertically or with depth, from which we can make these maps. And so the most common term used in seismic hazard analysis is VS30. So if this project was going to create one map, it would have been a VS30 map. And ideas on what practicing earthquake engineers should be doing with this map is listed on the right. But in combination with VS30 is the new concept of using site period is a complementary parameter to VS30 to properly account for site effects or anticipate what shaking amplification would be. And also usually a basin depth term or Z term that is also included in ground motion models. Basically, these three parameters, VS30, site period, and Z depth factors, are the current and also anticipated future important terms or parameters that capture site effects. So we made these maps to be useful to seismic hazard analysis now and also in the near future. So a quick summary again then is that we've made these maps because some of them were needed to make other maps. They're fundamental to assessing liquefaction or landslide hazards. You have to know the geology. We also made maps that try to communicate our improved understanding of the local site conditions. There was a depth to rock map available, of course, before, but it wasn't for the region as far as we have it now. And it wasn't based on as much information as it's been made to now. And then last group is that these are the non-negotiable metrics that are key to seismic hazard analysis. It doesn't matter if a community planner doesn't understand them or use them. They're needed for seismic hazard analysis in future. The first 6 we could discuss, but the next 6 or 7 needed to be locked in because of the use in seismic hazard analysis. Moving on to now we have this idea that the ground is susceptible to shaking amplification here, or maybe liquefaction should happen. But the question is, given what the expected earthquake shaking would be for this region, which comes from our national seismic hazard model, telling us where the seismic source zones are, what the recurrence rate of those earthquakes are, tells us what the shaking levels would be for particular return periods or for particular hazard levels, probabilities of exceedance. And so we made maps for 2 chosen return periods or 2 chosen levels of shaking intensity input. The other key piece to say is that the shorter return period, more frequent type earthquakes, that lower shaking intensity is more probable to occur more frequently. that level gets increased by 2 to 2.5 times by the second level of shaking intensity that we look at. The differences in the maps for the two different return periods is that the shaking intensity that we considered has been increased by about a factor of 2 to 2.5. So these level 3 hazard maps are telling us where and the amount of shaking that will be amplified, which we couldn't have answered before. We just knew it was susceptible to shaking amplification, but now we actually know how much, because now we have performed that seismic hazard analysis, considering that seismic intensity to tell us. And also we work on that in terms of liquefaction triggering and also landslide triggering. So we can say where and the inferred severity of these failures or hazards occurring related to the considered seismic intensity. So finally, we are considering what earthquakes are happening, the frequency at which the shaking intensity would be reached, the probability basically, and we choose these two different input shaking intensities. And in hindsight, I mean, you know, we doubled the number of maps essentially, which is kind of a horrible communication exercise or helps with confusion. But the whole point is you should be able to have, you should be able to contrast and compare them, and that should be helpful or beneficial. This level of shaking isn't as common, but it is rare, and maybe you want to design to that level, or maybe you want your community to be prepared to that level. But you also have access to another level of shaking intensity that was considered. I'm gonna tell you the details about liquefaction and landslide hazard potential mapping as quickly as I can, and so it's going to be fast and furious and complicated. But I'm trying to summarize it as much as I can, where essentially a level 3 seismic hazard analysis to calculate liquefaction and landslide hazard potential is that we have performed probabilistic liquefaction and probabilistic landslide hazard analyses. We have taken the ground motions that come out of a PSHA, or the rates at which the acceleration is occurring, and that gets tied through these conditional probability distributions, or the fact that we're accounting for what was the given intensity of shaking for that given magnitude of earthquake that comes out of the building code or out of the National Seismic Hazard Model. And then we calculate what liquefaction is in terms of the liquefaction potential index, and we calculate sliding displacements. And those are coming from embedded landslide prediction or sliding displacement prediction equations and liquefaction potential index prediction equations. It's like we replace the GMM for shaking with the equivalent for liquefaction and landslide. And so in the end, we come up with liquefaction and landslide hazard curves. We calculate liquefaction hazard curves for over 1,000 locations where we have cone of penetration and standard penetration or shear wave velocity information. And we've performed kind of a lookup table for all possible combinations of slope angle, slope height, and the groundwater table inside of particular slopes that guides us on the range of landslide hazard curves or sliding displacement hazard curves. So once we do that, we have the answer for the two chosen shaking intensities that we can make these maps for. We could make the maps for any shaking intensity level because we created the hazard curve, but for the purposes of the map project, we just generated maps for these two chosen shaking intensity levels. Quickly, you always knew the Fraser River Delta was susceptible to liquefaction. It's true that if we experience strong shaking around 0.1 G, 0.2 G, there is a very high liquefaction hazard potential, or the soil resistance is not high enough for that considered shaking level. And this is considering natural ground conditions. Of course, a lot of the delta is densified or ground improvement is done prior to building. An opposite case almost is that the landslide hazard potential map is all yellow or all low at the strong shaking level. we kind of need very strong shaking to trigger a lot of landslide failures. In our calculations for the slope angle, the older glaciated or Pleistocene age and cohesive clay-like materials that define a lot of the slopes. Last but not least, to quickly try to explain our shaking amplification hazard. This involved also sophisticated seismic hazard analyses, and that dynamic site response is accomplished for 55 locations. We have to select and scale time histories to the chosen shaking intensity levels for the 3 seismic source zones for 2 components of motion, so 66 time histories that are input for each of the 55 sites, resulting in almost 11,000 analyses or ground motion values for us to calculate what the amplification spectrum is, or what amplification is like with frequency or period. We can average that to make a representative amplification spectrum from which to determine the amplification value for a map. And where can we apply that same amplification for other locations that are similar is based on the parameters of VS30, site period, and post-glacial thickness of these locations. So we do not map our site effects just by VS30. We have to consider that the VS30 could be the same, but the thickness of the soil deposit and the velocities of that soil deposit will create a different site period. And knowing the thickness of that soil is very important for us to get what the right amplification is for that considered location. So we end up with 14 amplification spectra that explain what we anticipate amplification will be like at any given location in Metro Vancouver. And we map that out based on what we understood about the subsurface ground conditions based on VS30, site period, and post-glacial sediment thickness. Quickly, that the highest amplification is going to happen at the softest sites. We're going to see de-amplification when it's stiffer than our considered VS30 reference ground condition. But we're also going to see amplification at short periods for stiffer ground or thin sediments, and amplification at long periods when it's soft and thick. So here you see the short period maps that have been made for strong shaking and very strong shaking, are the 2 different considered seismic shaking intensity levels. When the sediments are kind of soft and kind of thin, we're going to get amplification, and that amplification won't be as strong at the stronger shaking level. And we're going to see not significant amplification and or a reduction in the amplitude of shaking where sediments are very soft and thick and soil nonlinearity is triggered and or liquefaction starts to be happening in these areas. That was all for one-dimensional site effects. We also were asked to include what the amplification or change to earthquake shaking might be because of the Georgia Sedimentary Basin underneath Metro Vancouver. And so we produce synthetic ground motions at a 250 meter resolution across Metro Vancouver. So for 6,400 locations, we're predicting ground shaking for over 50 earthquake simulation scenarios that we run, and we have a database of ground motions to determine what the shaking level is, and some pictures of the simulation that's running from the earthquake source. The waves propagate up into the basin, increase in amplitude, and are kind of stuck and reverberate within the basin structure. So we don't want to double count how much amplification happens from the basin. So we subtract what we would expect from one-dimensional site amplification to find out how much amplification is happening from the basin. So we find out the number, the amount that we can apply. But where does it apply? It depends on what the average depth is of the basin for the basin depth at that location. So we find out where we should put basin amplification and how much through this process. In the end, we end up with our final 2 maps 28 and 29, that are showing the amplification due to basin effects in Metro Vancouver. One thing is that, the maximum is around 2. because the Georgia Basin is quite wide and deep, 6 kilometers. Actually, sorry, wide and shallow, about 6 kilometers. And that's in comparison to, say, the Seattle Basin, which is super tiny, but thicker, about 9 kilometers. So they're very different. It's basin dependent. And for the first time, we got to see how much amplification is happening from the Georgia Basin. It's greatest or strongest in the southwest corner because you're at the deepest part of the basin. Interestingly, we don't need any basin amplification, or we don't have to add any because the VS30 is so low at these locations. It's already enough. But then as you get into the uplands of Vancouver, Surrey, and White Rock, the ground is stiff, and the 1D site amplification doesn't expect how much amplification is happening at long periods because the VS30 is quite high, but it doesn't know that it's still sitting inside of the Georgia Basin and is experiencing propagation of the higher amplitude surface waves as they propagate out of the deeper part of the basin. So we have to add that into our maps or into the amplification result. So the shaking amplification maps at long periods include both 1D and 3D answers. If you want to take the 3D away, you'd have to relate these maps to each other. And almost it's like the opposite effect is happening. We don't see amplification now happening in the shallow sediments because they don't amplify at long periods. And then we see high amplification happening in the deep, thick sediments, which it doesn't happen at short periods. So that's a long story, and it's a lot of effort and not that easy to have generated these level 3 shaking amplification hazard maps. Probably don't have time, but everybody always wants to know, how does this relate to the 2020 building code? Well, it's not easy to answer. It's not a fair direct comparison. You know, the building code is working with only one parameter, and we work with several. Or we try to make a much more sophisticated product because we know a lot more about the subsurface and what those side effects will trigger or result in. And so, you know, the building code is to design or have a similar safety level across the country, whereas our mapping is trying to express the state of the art that we have in our current knowledge of seismic hazard and subsurface ground conditions. Last is that the national scale mapping does not have any idea about the 3-dimensional Georgia Basin. It is inherent inside of VS30, as we know, and it's okay at the eastern edge of the Fraser River Delta, but it's not enough in other places. And our maps are the only source currently that can express that information to you. Our amplification results for those 14 classes that we looked at are now compared to the 2020 building code anticipated average result in red dashed line. So sometimes our colored lines are above the red dashed line. So we anticipate higher amplification, mostly at short periods, because we see resonance happening, which isn't really accounted for very well by the inherent site amplification model or the inherent type velocity model inside of the building code or the GMMs. Whereas at other cases, we see that we don't anticipate as high amplification for very soft and very thick locations. And how that looks on a map is that we would see a difference in the amplification that we anticipate from the building code, where there's relatively thin soils that have resonance or increase in amplification at particular periods that are kind of missed or smoothed out by the building code. And then we also see quite a bit more reduction in shaking amplitude de-amplification, primarily in the softer, thicker sediments, say the Fraser River Delta, that is not included in the building code or the same amount. So we're not done. We keep working on the eastern communities in Metro Vancouver. We were out last summer, a team of 8, collecting more measurements to ensure we have geodata for those locations. So hopefully now you understand what went on and how we achieved so many maps, and that not all the maps are the same, and they can't all be treated equally. Some of them are much more sophisticated than others. And nobody's ever made level 3 hazard maps or, solved what the actual ground shaking or what the actual trigger, whether liquefaction or landslide is actually happening from the seismic hazard intensity. We hope this is going to be a useful type of product in future. Normally, the code would do this or practice would do this. Normally, seismic micronization mapping projects would have stopped at level 2 susceptibility. But we're hopeful that we have created a new communication about what seismic hazard is in Metro Vancouver that can lead to changes in design, retrofits, mitigation, and general living in Metro Vancouver. Thank you.
Well, thank you very much, Sherry. I really enjoyed that. I hope everyone is same. Now we are open for questions, if you don't mind. Well, the first question is, can you show us how to get access to these maps and how to use them? Probably this question came before your explanation about the National Building Code VS30, but please go ahead and give us more explanation if you have.
I will just reshare this one slide. The website link at the bottom right of the slide is where the map files are officially published. But you will also have access to the maps in the future from GOBC or through the provincial government. And currently, you can also go to our project website and look at the maps online. You don't have to download them. You can play with them or look at them online before deciding whether you want to download it or not. So the project website is metrovanmicromap.ca. You would go to the open data portal, and then you can choose to launch the map viewer. Or you could click on accessing the published maps here. You could get to the link.
Okay, and is it possible to use these maps to identify the bearing capacity of soil?
There is no map that maps bearing capacity of soils, but there are are two maps that kind of explain geology. Is that there's a geology material type map, but then there's also the thickness of post-glacial sediments map. And that map is telling you how much sediment you have to go through before you hit something of stiff enough good foundation. Normally, standard penetration test result or a cone penetration would have hit refusal. It's kind of like a refusal map. Therefore, it also tells you maybe the length of a pile that you might need, or at what depth can you anticipate the foundation for a structure should be at. Now, our liquefaction susceptibility table gives you the average cyclic soil resistance. And so there's an expression of how stiff that geologic polygon is in terms of its subsurface ground conditions. So currently, we do not give you access to bearing soil capacity as a parameter, but there's other parameters that are close, that are available in the maps currently. And then eventually, the geodatabase would be available. However, we do not have bearing capacity as a column that we tracked. It would have VS, it would have the cone penetration resistance, it would have the standard penetration resistance. Other measures about how stiff the ground is that you could relate to bearing capacity.
Thank you very much. Let me ask my question to you, if you don't mind. I was wondering how will you update the seismic maps in future? For example, every 5 years, 10 years, do you have any plan according to the new outcomes from the research projects?
This is a very good question. I mean, this type of work has been going on for cities in Canada since the 90s, right? So there's an Ottawa map, there's a Montreal map. And so our team has spent 7.5 years working with the geodata, but let's be honest, we had all that geodata assembled only a few years ago. And I anticipate it's still going to take us another 10 years to fully understand and probably make revisions as us, our research team. But I'm an academic and I couldn't possibly do everything. So we are releasing the data with our publications. And so right now there's CPT data. Our CPT database is available online. So I'm sure there's someone doing machine learning and AI of CPT data under Metro Vancouver as we speak. And so I anticipate that, in the next 10 years, there's going to be a lot of new advancement made from access to the outputs that this project has produced. Our funder is the provincial government, and our project will end in 2026. It's my own research that would continue going on for another decade. Others will be using that data, but there is not a current plan with the provincial government that they're going to fund that this gets updated every 5 or 10 years. That's why the level 2 maps are pretty awesome in that they don't need to be updated every 5 to 10 years necessarily. But the level 3 maps that consider the seismic intensity or the shaking, when there's a new building code, they need to consider that. So they need to be regenerated in that kind of schedule.
Thank you very much.
Mhm.
I haven't received any more questions. Oh, yeah, one question from Dr. Cassidy. Maybe it's a comment, it's a long question or comment. I'll read it. Outstanding presentation and work. Thank you, Sherry. My question. You mentioned that topographic effects were not considered in this study for good reason. In your work, did you encounter any results that might suggest topographic amplification? For example, North Vancouver, Kew Park, Little Mountain, etc. Any plan to pursue topographic amplification in the future? Stronger shaker at the top of bedrock hills, mountains may be an important factor for potential landslide generation, which may in turn generate localized tsunamis. Yeah, more or less about the
Yeah,
topographical amplification.
this is a good question. I mean, essentially the project didn't answer everything that could be answered, or hopefully now that the maps and the layers are available, anyone can look into this in future. I could see that, a future research student would look into, local tsunamis being generated from landslides. My team, we've been working on topographic amplification by including topography in the 3D wave propagation simulations. The success there is at a master's level that, yes, we did it, but we're still working on being sure of the answers to include it in mapping in future. But it's not that far away. I would say, in 5 years, 10 years, it could be included. As John knows, we were modeling the basin effect about 10 years ago, and then finally here we are. We're displaying it and communicating it out, and hopefully it's going to be incorporated. So I can see topography coming involved in the next 5 to 10 years. And then this is a good question, and it chips away at a little hidden detail that we did everything at once, and that's too bad, because it would be nice to take what we get from the shaking amplification output and put that into the liquefaction and landslide assessments. Unfortunately, we didn't know the shaking amplification result when we had to start with the inputs for liquefaction and landslide. So the inputs to liquefaction and landslide is based on the 2020 code shaking amplification values or shaking amplitudes. But we know those aren't the exact same that we would predict. And so that's a little hidden error or aspect that would be and would trigger this revision of the liquefaction and landslide maps. That now that we know, now that we've finished level 3 mapping, we should be looking at whether the AMAX values or the PGA values that were being put in as input are appropriate to what we think would be the right level for the region.
Okay, so another question related to the 3D mapping. Did you try to build a 3D geological modeling for the region?
Yes. We have one version that's published in the journal Seismica right now by Adhikari and Molnar. It's our first generation of a three-dimensional model, and it's kind of in two pieces. One is what the geology told us as blocks, and then also what we think the velocity horizons are. Then I've had a research associate work on regenerating our 3D model, and we're preparing a Geo Manitoba conference presentation to explain that. We've been focused on our contractual obligations of making 29 maps available for the end of 2024. We didn't have to explain very well how we did it. And so we're working on getting that out soon.
Thank you very much, Sherry. And thank you all very much for attending this webinar. For your information, a video of this presentation will be posted to the Canadian Association website and will be accessible to all members. Please note that you will be receiving professional development hours certificate automatically if you registered and attend the most part of this webinar. If you didn't receive it in a month, please feel free to contact us by sending an email to the Canadian Association Secretary. Thanks again to Dr. Molnar for a great presentation, and thank you all for joining us and attending this webinar. Now we are closing this session. Thank you. Have a good day.
Thanks, everybody.
Thanks. Bye.